Okay, so today we're going to do 2 lessons in one. We're going to explore how fractional exponents work and how negative exponents work. Now, we're going to do both lessons at the same time, but I'm actually going to start at 4.5. So can everybody go to 4.5? That's where we're starting. And I'm going to start with the rule. So here's the rule. Here's the way that this works. A base to some negative power, some negative number, I'll call it negative n, is equal to 1 over x to the n. That's the rule. Now I'm going to try to convince you of why that rule is true. So, oh, we're fuzzy. That's better. So there we go. Our rule is x to the power of negative n is equal to 1 over x to the n. So now I'm going to try to convince you as to why that rule is true. So, I'm going to try to activate some grade 9 knowledge. I used to tell my grade 9s that this piece of information here was the first really grown-up math thing you ever did. Because it's the most abstract thing you do in grade 9. Most people think of an exponent like, well, 2 to the 3, no problem. I can imagine that. It's 2 groups of 2 groups of 2. And that makes 8. Why the heck does 2 to the power of 0 make 1? This rule tells us that anything to the power of 0 makes 1. But why does it exist? Why is that true? I can't even imagine taking 2 times itself 0 times. And if I can, why is it 1? Well, because that's what the rules tell us it has to be. It's not based on a physical reality. It's based on logic, reason, and rules that I already know are true. Here's how I explain it to my grade 9s. Let's see if we can focus on this a little bit. Suppose I play with 2 some more as a base. 2 to the power of 5. Well, that's 2 times 2 times 2 times 2 times 2. That's 32. 2 to the 4, 16. 2 to the 3, 8. 2 to the 2 is 4. 2 to the 1 is 2. Okay, let's take stock for a second. What is happening on the right side every time I go down a step? I'm dividing by 2. So the next answer had better be 1, because that's what 2 divided by 2 is. And that's why 2 to the 0 is 1. And notice, this would happen no matter what I picked for a base. If I was using 10s instead of 2s, no problem. 10 to the 5 is 100,000. 10 to the 4 is 10,000. 10 to the 3 is 1,000, because every step I'm just taking away a 0, i.e. I'm dividing by 10. 10 to the 2 is 100. 10 to the 1 must be 10, so 10 to the 0 must be 1. So hopefully your grade 9 teacher showed you this and didn't just say, hey, this is a rule, deal with it. Because I think rules are easier to understand if they make sense to you as to why they exist. This rule exists, because no matter what base I start with, this will always happen. When I hit this part of the pattern, I'll end up dividing a number by itself. Now, there is kind of one exception. Actually, I don't like to use the word exception. This isn't ELA. It's not an exception to a grammar rule or anything. There's a rule that counts before this rule. Notice that this x here can't be 0. Because if I said, what's 0 to the 5, you'd say, well, it's 0. And if I said, well, what's 0 to the 4, you'd say, well, that's 0. 0 to the 3 is 0. Notice, I'm not dividing by 0 every time I go down a step, because you can't divide by 0. Remember that? Can't break that rule to have another rule. So this is true if and only if x is any number but 0. It even works for decimals. I always point this out to my grade 9s, even though in grade 9, you don't actually have to play with decimals when you do powers. But suppose I had 0.5 to the power of 3. That'd be 0.125. 0.5 to the power of 2 is 0.25. 0.5 to the power of 1 is 0.5. Notice every time I go down a step, I'm still doing the same thing. I'm dividing by 0.5. So 0.5 to the 0 has to be 1. So that's the rule that you learned in grade 9. Here's what I want you to do now. I'm going to go back to, let me start that little pattern over. So let's play with 2 again. So 2 to the 4, we'll say, we'll start there, is 16. 2 to the 3 is 8. 2 to the 2 is 4. And 2 to the 1 is 2. And as you learned in grade 9, that's 1. What if we don't stop there? What does the left's column do? Well, it takes 1 away from each exponent, right? So logically, that's my next exponent. What's the other side? What's 1 divided by 2? It's a half. Now again, it seems to be a weird thing to say, I'm going to times 2 by itself negative 1 times. But that's the way I perceive the rule for the exponent negative 1. 2 to the exponent negative 1 makes the fraction 1/2. Keep the pattern going. What's a half divided by 2? Quarter. What's a quarter divided by 2? An eighth. Now let's take a look at something here. What do you notice about these two things here? 2 to the 3 is 8. 2 to the negative 3 is an eighth. What do those things have in common with each other? How do they relate to one another? What is the relationship between 8 and 1/8? They're reciprocals. And that's why it even says at the top of your thing, negative exponents and reciprocals. Negative exponents make reciprocals. So let's use that one as our first example. 2 to the negative 3 is the same as saying 1 over 2 to the 3. It's 1/8. If 2 to the positive 3 is 8, 2 to the negative 3 is 1/8. You can think of positive exponents as repeated multiplies. 2 to the 3 is 2 times 2 times 2. 2 to the negative 3 is repeated divides. It's like saying 1 divided by 2 divided by 2 divided by 2. And that's how negative exponents work. I can show you one other cool little way to prove it. I can also show you your quotient law. Let's evaluate that. 2 to the exponent 4 is 16. 2 to the exponent 6 is 64. Simplify that fraction for me. What's 16/64ths? I heard somebody say it. You're right. A quarter. Okay, here's something else. Do you remember back in grade 9 again, you learned a power law. What do you do with exponents when the base is the same and you're dividing them? You subtract them. So this is 2 to the 4 minus 6, which is 2 to the negative 2. So now think about it. If this thing equals that, and the same thing equals that, then these two things have to equal each other. So that's my rule. X to some negative power is 1 over x to that same power without the negative. That's our rule. Let's use it. Example 1a. 3 to the negative 2. Let me move this out of the way. 3 to the negative 2 is like saying 1 over 3 squared. See what I did is I actually used that negative and it made a reciprocal. So now it's gone. I used it already. So this is 1/9. This is like saying 1 over 7 squared. So that's 1/49. This one, now that negative is in the bracket, which means it's part of the base. But that base ends up down here, squared. And what happens when you square a negative? You get a positive, because a negative times a negative is a positive. So there we go. So there's our first 3. Okay, those were easy. What if the thing we're playing with has a base that's a fraction? Okay. So this is now, I'm just going to use my rule. It's 1 over 10/3 cubed. Okay, well, let's expand the cubed. That's 10 over 3 times 10 over 3 times 10 over 3, so that's 10 times 10 times 10, that's 1,000. And 3 times 3 times 3, that's 27. But what do I do with that? Well, remember back to your fraction rules. What happens when you divide by a fraction? Oh, am I off the screen? Oh, no, I'm fuzzy. Thank you. I don't know why it won't autofocus for me. Okay, anyway. The limits of my technology. Anyway, like I was saying, how do you divide by a fraction again? Yeah, I heard somebody say it. You multiply by the reciprocal. So this is 1 times the reciprocal. So this is just 27 over 1,000. So can I point out to you, it should always work like this. We can kind of shortcut that. Notice that this negative makes the answer reciprocal. Why don't I just start by reciprocaling it? And the act of reciprocaling it is me using that negative. So the negative is gone now because I reciprocaled the base. And what's negative 4 cubed? Negative 64. And what's what's positive 3 cubed? 27. So it's negative 64 over 27. All right. Now let's look at f. The negative exponent is in a denominator already. So this is like saying 1 over 3 to the 4. See if you can get your head around that. So that's going to be 1 over 3 times 3 times 3 times 3. That's 81. Somebody double check my mental math. I think I'm right. Now, again, if I'm dividing by a fraction, I'm multiplying by its reciprocal. And the reciprocal of 81, or sorry, the reciprocal of 1 over 81 is just 81 over 1. Please notice I never bother writing over 1 in a final answer. Okay, so there we go. That is the start of 4.5. And if you're wondering why I'm not continuing to the next example in 4.5, it's because, well, take a look. It's got something in it that we haven't learned how to deal with yet. It's got a fractional exponent. So can we go back now to 4.4? And let's talk about fractional exponents. All right. Fractional exponents. Okay, where's my list? There it is. 2 to the 4, 2 to the 3, 2 to the 2, 2 to the 1. Where's 2 to the half? Again, this is a very abstract idea. I'm going to times 2 by itself a half a time. Well, it's somewhere between here and here, so it's obviously an answer between 1 and 2. Well, you know what? I'm going to try it on my calculator. Okay, I'm going to use this calculator. This one's kind of fancy, but I'll use it anyway. What is 2 to the power of, and I don't want to enter a fraction, so a half is 0.5, right? 0.5. That number look familiar? Where have you seen that number before? That's the square root of 2. And that's my rule. The rule is the nth root of x is like saying x to the exponent 1 over n. And I'll even put it in words. Radicals are fractional exponents. That is true. So for my first example, 2 to the exponent 1/2 is the same as the square root of 2. Let's pick one that we could evaluate if we wanted to.
Thank you.
Thank you. How about we want 4 to the exponent 1/2? Well, that's like saying the square root of 4, which I know is 2. What if I wanted 8 to the 1/3? That's like saying the cube root of 8. See how this number here, the denominator of the fractional exponent, it's the same as the index. Remember, this does have a 2 on it. I just don't usually bother writing it down. I know it's there. There, I'll make it invisible too. So the cube root of 8 is 2. Let's just double check that. That seems like a strange thing. Again, 8 times itself 1/3 of a time is 2. Let's see if the calculator agrees with that. 8 to the power, I guess I better enter this as a fraction maybe, or I'll enter it as a divide. 1 divided by 3. There we go. Close brackets and hit equals. Yep. It's the same thing as cube rooting. Once again, it's one thing to memorize the rule, but it's easier and it's better for you if you kind of know where it comes from, or if at least I can convince you that it has to be true. Here's my argument. Check this out. How much is this? Give me an answer for. Simplify that for me. Let me see if I can make that clearer again. There we go. Yeah, that's just x. Why is that just x? Well, because this is how math works. If you take a number, say you take 5 and then you add 2 and then you minus 2, well, you get 5 again. If you take 5 and you times 2 then divide by 2, you get 5 again. Anytime you do an operation to a number, then right away you undo it, you get the number back. So if I take any number x, I square it, then I square root it, I should get x. So that's logical. But let's think about it this way. The square root of x squared is like saying the square root of x times x, right? So now, let me put it to you this way. This, we've decided, is x. This, we learned in our last chapter, I can think of as the root of x times the root of x, for the same reason that the root of 20 is the same as saying the root of 4 times the root of 5. Therefore, it's 2 root 5. I can split up a radical into 2 multiplied radicals of its factors. So this thing and this thing are the same thing. So x is equal to that. True? Think about this now. X means, of course, x to the power of 1. If I asked you to fill in those blanks, oops, I meant times. That's a times. If I asked you to fill in those blanks, and those blanks have to be the same number, what's the only possible number those two things could be? Now, careful. What do you do with exponents when you're multiplying and they have the same base? You're adding. So what's the only number you can add to itself and get 1? It has to be a half, doesn't it? So this is a half, this is a half. So look at this. This is equal to that, which means that these two things equal those two things. So logically, the square root of x has to be the same as x to the 1/2. So as weird as it is to think about, we now have fractional exponents, but we've seen them before. We've seen them as radicals. All right, so let's play with some radicals. I don't even know what to put for example 2. I'm looking ahead. How about we go, I don't know. How about we go backwards from example 1? Let's start with the square root of 64, and let's express that as a fractional exponent. Well, then that's 64 to the 1/2. Let's do one with algebra. Suppose I had the square root of 3x. Well, then that's the same thing as saying 3x to the exponent 1/2. All right, let's do some evaluating now. Evaluate 9 to the power of a half. Well, that's the same as saying square root of 9, which is 3. And again, I got all fuzzy. Yep. 25 to the 1/3 is the same as saying, what's the cube root of 125? Okay, what number times itself 3 times is 125? 5. All right. Look at example 5. 4/9 to the 1/2. Maybe if I move this closer, it will help, eh? Oh yeah, sure. Is that better? Let's see if it stays unfuzzy longer. 4/9 to the 1/2. That's the same as saying what's the square root of 4/9. Now I can distribute a square root through a divide or a multiply. So that's like saying what's the square root of 4 divided by the square root of 9. That's 2/3. And this one, this is like saying what's the square root of 0.49. So what number times itself is 0.49? The answer is 0.7. I had somebody this morning saying, wouldn't it be 0.07? No, think about it. When you square root a decimal, you actually get an answer that's bigger, because when you take a fraction of a fraction, you get smaller. So think about it. 0.7 times 0.7 is like saying I want 7/10 of 7/10. So I get a number smaller than 7/10. Right? Okay, so that's example 6. Example 7. 8 to the 2/3. Okay, this is fun. I love this. This is one of my favorite parts of the whole grade 10 course right here. There's 2 ways I can express this. I can express this as the cube root of 8 squared, or the cube root of 8 squared. Now, if you were just listening to me, it sounded like I said the same thing. But look at what I wrote down. Their order is different according to BEDMAS, right? This would be, well, that's the answer I guess we're looking for. It's written as a radical. But let's say that we evaluated it. If I said, okay, the cube root of 8 squared, I treat the radical like a bracket and I have to do its inside first. What is 8 squared? 64. So what's the cube root of 64? What number times itself 3 times is 64? 4. What about this one? Well, this one's saying that I'm cube rooting 8 and then I'm squaring it. Well, what's the cube root of 8? 2, and then I'm squaring it. Notice it's the same thing. Why is that? Why am I allowed to pick which order I deal with this sort of 2 parts of this exponent? Well, because I'm not violating BEDMAS by doing it. Watch this. 8 to the 2/3 is like saying either 8 squared times a third, or it's like saying 8 to the power of 1/3 squared. Because remember what happens when you take a power of a power? You times them together. So that makes sense that it doesn't matter what order I times things, right? 2 times 3 is the same as 3 times 2. They're both 6. 2 times a third is 2/3. 1/3 times 2 is 2/3. It doesn't matter what order. But if I look at it this way, I'm looking at this. And if I look at it this way, I'm looking at that. But I just figured them out. They're both 4, so it doesn't matter. It's the same number either way. But the fact that I can pick which way I think about it allows me to do some interesting things when I'm evaluating. So we'll get to that in a sec. Let's just keep going on these examples. First, let's just write these as radicals. So this one's going to be the 5th root of 40 cubed. This one's going to be the square root of x cubed. And this one's going to be the 4th root of w to the exponent 5. Now, I can't do anything with those. I don't know what x and w are. But I could evaluate this one too. And in fact, I'm going to, and I want you to try to evaluate it with me. So if you've got your calculator, let's see if we can find our radical buttons on our calculator. I have a few different calculators here. I'll stick to these two. Anybody got a calculator like this guy? Or something similar to it? Okay, if I would like to do that calculation, the 5th root of 40 cubed, I'm going to actually do the 40, I'll do the 40 cubed first. I have a cubed button. There it is. Now I need the 5th root of that number. Where is my 5th root button? Well, you don't have a 5th root button. You have, can you see that there? Or wait a minute, am I looking at the right place? No, I'm not. Where are you? There, sorry. On your exponent button, the shift on this calculator says x root y. So that could be any root you want. 3rd root, 4th root, 5th root, 6th root, a billionth root, whatever you want to type in. So this is going to be, I want the 5th root of, what was my answer again? I already forgot what it was. 64 and then 3 zeros, right? And there it is. This evaluates to 9. It makes sense that it's irrational. 9.146, blah, blah, blah. Notice again, if I'd have punched it the other way, if I'd have done the 5th root of 40 and then take my answer and cube it, haha, same answer. I love that. I amuse easily. That amuses me. Anybody not find their root button on their calculator? I see a few confused faces. No, seriously, put up your hand if you can't find where your root button is. Let's see if we can get your calculator. Here's the fancy calculator again. So let's try this one again. So we know what we're supposed to get. So I would like the 5th root. Oh, see, I typed it wrong. I have to type the button first this time, then fill in the numbers. And then this one's really fancy. I can actually put 40 to the power of 3. Look at that. I can do that all at once on this guy. And there it is, 9.146. Anybody got a very basic calculator where it doesn't show you what you're actually typing in as you type it on the top? Can I borrow yours? Bring it on over. In case anybody's watching this video and they have a calculator like this guy, this one takes a little more work, but it still can do the job. Again, I can do it either way. I can go 40 cubed, and then I want the 5th root of that. So now that it's on the screen, my xth root button is here. It's the shift on my power button. So I go shift, that button, and I want a 5th root, so I type a 5. And there's that number. Or, again, I could have taken the 5th root of 40 and cubed it. I get the same answer either way. Thanks. Okay, I think that probably gets most of your calculator's types of button punches out of the way. All right, keep on going with the examples here. In exponential form, what's that guy? Well, this is like saying 3 to the 5 to the 1/3. What do I do with those exponents? I times them. What's 5 times a third? 5/3. Now, if that makes total sense to you and you want to skip this step, I don't mind. It means that you would know right away that this is just 3 3 halves. This one is just 7 quarters. And this one is 4 thirds. Give you a sec to catch up to me. Okay, so that's example 7 and 8. There's a couple more in this one yet. Example 9. What's the difference between the instructions on the last one and this one? This one wants a number. It wants an answer. It doesn't want me to leave it as a radical. It wants me to figure it out. So now I have a choice. This is like saying either the square root of 4 cubed, or it's like saying the square root of 4 cubed. Which one's easier? This one that probably doesn't matter. I can cube 4, it's 64, so the square root of 64 is 8. Or the square root of 4 is 2, 2 cubed is 8. Either way, I got the right answer fairly easily. But look at the next one. Would you rather think of this as the cube root of 27 to the 4, or as the cube root of 27 to the 4? What would you rather do? Take 4 27s times together and then try to cube root that number? Or would you rather try to cube root the 27 and then multiply that number by itself 4 times? I don't know about you, but I have no idea what 27 to the power 4 is. 20 to the power 4 would be, what, 160,000? So it's going to be big. I have no idea what that number is. But this number, that I can handle. What's that going to be? That's going to be 3 to the 4. 3 times 3 times 3 times 3 is 81. So there was an advantage to thinking about it this way. Because yes, we will test you with this stuff without your calculator. Dum dum dum. Okay, everybody good? Let's try some uglier ones. Look at that one. I'm again going to think cube root negative 27 and then square it. What number times itself 3 times is negative 27? Negative 3, very good. But notice it's still the base and I'm still squaring that base. So my answer is positive 9. Okay. My morning class decided they'd rather look at this like a fraction. And I said, mark this in your calendar. This might be the first time in your whole life that you finally realized fractions are easier to work with than decimals most of the time. Because I don't know about you, but that's always, can't we do this in decimals? No! For once, can you see the beauty of doing this as a fraction? Because as a fraction, this is 1 over 100 to the 3 halves. Get it? 1/100th. And that's an easy number to square root. What number times itself is 100th? No? What? Okay, yeah, well, the top, sure. If you want to split it up, we can do that. So the top is 1. What's the bottom? What's the square root of 100? And then cube everything. 1 times 1 times 1 is 1. 10 times 10 times 10. And this says 1,000. I think it's easier to work that one fractionally than it is decimally. But if you did want to work with the decimals, you could. This is, again, 0.01 square rooted, then cubed. And you can realize that if you, what number times itself makes that? Well, it'd be 0.1. And then what's 0.1 times 0.1 times 0.1? 0.001. Same answer, both 1,000th. I don't really care which way you think about it. If they gave you decimals, you can give me a decimal answer. All right, so that was example 12. That takes us back to 4.5. Now, where did we leave off? We're putting it all together. We've got a negative and a fraction. So let's do it one at a time. What does the negative do to this? It reciprocals it. There, negative's gone. What does the 1/3 do? It cube roots it. What's the final answer? 1/2. Isn't that cool? All right, now look at this guy. What does the negative do to this base? It reciprocals it. What does the exponent 1/2 do? It makes it a square root. What's the square root of 36? And what's the square root of 25? Done. All right, couple more. Again, I'll deal with the negative first. What does a negative do to the base? It makes it its reciprocal. Actually, this exponent should be on the numerator too, but you can take 1 to any exponent you want and it'll always be 1. 1 times itself any number of times, even a fractional number of times, will still be 1. So that's why I haven't bothered saying it like this, even though this is actually still true. I kind of skip that step and go right to here. Here's where the action is, down here in the denominator. So now, would you like to cube 16 and then square root it? I can square 16, but I don't think I can cube it in my head very easily, so I think I'd rather square root it first and then cube it. There you go, 1 over 64. Okay, I'm going to assume that example 5 was a typo. Can you find the typo in this picture? What's wrong with this picture? Well, if I wanted to cube root these two numbers, 125 is a perfect cube. Is 63 a perfect cube? No, so I have a feeling they meant, can you please change it? I think they meant this to be a 64. Somebody typed it wrong. So, once again, I'm going to deal with the negative first. Bye-bye negative. I am going to then cube root this. And then I'm going to take it to the power of 4. 5 times 5 times 5 times 5 is 625. 4 times 4 times 4 times 4 is 256. And there it is. Okay, so, oh, I'm off the screen. So there you go. You've got notes that you can ponder, and there'll be a textbook assignment for that.